In this video, I will introduce you to my research topic, which concerns the electrodeposition and characterization of iron-based metallic coatings with a sustainable approach. My research is part of SELECTA project, which is a Marie Curie innovative training network funded by the European Community under Horizon 2020. Let's start explaining what is electrodeposition. As we can see from this schematic representation, electrodeposition process involves the use of an electrolyte to transfer the species of interest, two electrodes, and an external power supply to drive the deposition process. In this example, we are applying a certain current input to accelerate the dissolution of copper anodes and to drive the dissolved copper ions to be deposited at the cathode surface. So, after a certain time, our cathode surface will be covered with a layer of copper. The main advantages of electrodeposition process are that it is a simple and cost-effective setup with fast deposition rates, mostly performed at ambient temperature, and that allow to deposit relative thick coatings and to fine-tune properties of the deposits. For these reasons, we find electrodeposited coatings in different application fields, as protective coatings against wear and corrosion, or in magnetic applications, such as magnetic actuators or as recording devices. Within the field of electrodeposition, the goal of SELECTA is to integrate technological progress with environmental concern. To achieve this goal, we are working on developing green electrochemical synthesis and characterization of innovative metallic alloys to be implemented as advanced protective coatings or electromechanical and magnetic systems like MEMS and NEMS. Our sustainability approach to reach this objective consists in employing environmentally friendly baths and by depositing alloys without scars or toxic elements. If this will be the general case, most of the common and good performing coatings that are currently present in the market will be not good enough anymore. We want to find a better alternative. SELECTA projects involves the work of 15 different PhD students, divided between the 9 main project institutions, all working together to reach our goal.
I hopefully gave you an overall picture of what is SELECTA project, but now I want to focus on what is my research work within SELECTA. As I said in the beginning, here at Chalmers University of Technology, my research is focusing on the characterization of iron-based electrodeposited alloy, like this one. This is an iron tungsten coating deposited on a copper surface to be used as a protective coating and to be used possibly as an environmentally friendly replacement of hard chromium coatings. In hard chromium coatings, it's not the chromium per se the problem, but the use of the hexavalent chromium for its deposition, which is strongly cancerogenic, and for this reason it has to be replaced. I don't work directly with the deposition of the iron tungsten coatings. This is done by my colleague Aliona Nikolenko at Vilnius University. I study the structure and the properties of the material. So let's take a closer look.
As shown by XRD analysis, the crystallographic structure of the as-deposited iron tungsten coatings change with increasing tungsten content, passing from a nanocrystalline structure, which is found for the 4 atomic percent tungsten sample, to an homogeneous amorphous nature for the 24 atomic percent tungsten sample. The thermal stability of the coatings, together with the heat treatment effects on the mechanical properties of the iron tungsten coatings, has also been studied. Here I include the results from the coating with 24 atomic percents of tungsten. The sample retained its amorphous structure up to 600 degrees, where a partially crystallized structure is observed. At 800 degrees, we observe the formation of different crystalline stable phases, but the material is still not fully crystalline, as shown by the broad shoulder visible in the XRD spectra. The hardness of the coating upon annealing keeps increasing, and it reaches its maximum at 600 degrees with 16.5 gigapascal. which is a very good value, especially when compared to the hardness of our chromium, which in the as deposited condition, as we see, is around 1200 vickers, which roughly correspond to 12 gigapascal. But the hardness of the material keeps decreasing when the material is operating at higher temperature. As a summary of the results of the work done, we saw how the iron tungsten coating reaches in tungsten is characterized with a high thermal stability and with an as-deposited hardness comparable with the hardness of our chromium, and its hardness can be further increased upon annealing up to a maximum value of 16.5 gigapascal. The results obtained are promising. What will follow now will be to study the corrosion properties of the iron tungsten coatings. Thanks for listening to this presentation.